Hello. In this video, we're going to be talking about how to solve homogeneous linear difference equations. So, to start out with, we have this problem here. The problem is to find all solutions to this homogeneous linear difference equation right here. So a sub n is a sub n minus 1 plus 2 times a sub n minus 2. Notice that we do not, in this case, have initial conditions. That is something we could add on to the problem, and it would just be an extra step at the end. So let's see if we can come up with all solutions to this. So the first step we're going to take is to rewrite this in our linear difference equation format. In other words, we're going to move everything to the left. So rewrite as a sub n minus a sub n minus 1 minus 2 a sub n minus 2 is equal to 0. Okay, the next step may sound a little strange, but we are going to make a guess. Okay, well, how do you know what to guess? Well, a lot of smart people, smart mathematicians, have worked on these types of problems before, and we're going to take advantage of their expertise. An educated guess is that a solution might exist of this form. So a sub n is r to the power n for some particular r. Okay, in this case, we're going to be able to get away with the fact that r is a real number. In some cases, you might actually, even if you're only looking for real solutions, you might want to look at complex values for r. Okay, so how does this help us? Well, let's just try to plug it in. So let's plug in our guess. If a sub n is always equal to r to the n, then this is just going to be r to the n minus, well, the n minus first term of the sequence must be r to the n minus 1. And the n minus second term of the sequence is r to the n minus 2. And this must be equal to 0, as long as n is at least 2. Alright, so if this is true, we can now factor out some of these factors of r. All three of these terms have some factors of r in common, so I'm going to factor that out. And all of them have at least n minus 2 r's. So I'm going to factor out r to the n minus 2. Okay, and what's left when we do that, we have n here. We pulled out n minus 2 of them, so there's 2 left. Here there's n minus 1, we're pulling out n minus 2 of them, and so there's 1 remaining. And here there's n minus 2, we're pulling out all of them. So there's no r's left in the last term. Okay, why does it help us to factor this? Well, for standard solving polynomial reasons, if you can factor a polynomial that's set equal to 0, then that means that one of the factors must be 0. So either r to the n minus 2 equals 0, or this other piece, r squared minus r minus 2 is equal to 0. Okay, so let's look at this first. We're saying r to the n minus 2 equals 0. Well, that just means that r must be 0, right? If you raise some number to a power and get 0, the number that you started with, the r, has to be 0. Okay? And saying that r is 0, remember a sub n, the sequence, the formula for the sequence is r to the n. And if r is 0, then a sub n is always equal to 0 to the n. In other words, a sub n is always equal to 0. That is the 0 sequence, and we already knew that the 0 sequence was a solution to this because it's a homogeneous linear difference equation, and the set of solutions form a vector space, which must include the 0 vector. Okay, so the 0 solution is not new information, so we don't care about this. This will always work, and it's just not giving us any information that we care about. So we're going to ignore that. Over here, we have r squared minus r minus 2. So we're always going to get this piece that factors out, and we're going to get a nice looking polynomial that we can deal with over here. And this equation has a name. This is called the auxiliary equation. Okay, so this auxiliary equation is something we always want to consider when we're trying to reason out how to solve these things. So for example, this polynomial right here has two distinct real roots, okay? And that means the solution is going to look a particular way. If it falls into one of the other cases, such as having exactly one real root with multiplicity 2, we have to do something slightly different in our solution. And there's a sort of a difficult case where it does not have any real solutions. So that's the case where we might want to look at complex values of r in order to solve this. Okay, so for right now, we're in the real case, so we can say, we can factor this. So let's do that. So we get r squared minus r minus 2 equals 0. That's the same thing as saying r minus 2 times r plus 1 equals 0. And that means that either r minus 2 is 0 or r plus 1 is 0. If two things multiply together to be 0, then either one is 0 or the other is 0. Okay, well this simply says that r is equal to 2, and this says that r is equal to negative 1. So if r is equal to either one of these two things, then r minus 2 times r plus 1 will be 0, which means that this will be 0, which means that this will be 0 because it's something times 0. That means that this will be 0, which means that this will be 0, and our linear difference equation will be solved. So what that means is a sub n is equal to 2 to the n is a formula for a solution to this. And a sub n is equal to negative 1 to the n is another solution. Okay? And I'm going to give these two solutions different names. I'm going to call one of them x sub n and the other one y sub n. And now I want to say that these two solutions are linearly independent. Okay? So xn, yn is linearly independent. Okay. So how do I know that? Well, one thing I can do is I have two vectors, so as long as one is not a multiple of the other, then we're good. But in general, this might be a higher order. So if this went up to a sub n minus 3, an order 3 difference equation, then this would be a cubic polynomial. We'd end up with 3 answers here, and we wouldn't be able to do that. So let's go through this process. So I'm going to show that this is linearly independent by saying let's take this C1 times the first one plus C2 times the second one equal to 0. And I'm going to try to show that the coefficients must be 0. So if this is true, then the coefficients must be 0, which is exactly what it means to be linearly independent. So how do I show that these coefficients must be 0? Well, this is an equation that is true for every value of n. That's the idea. So I can just plug in some values of n and see what I get out. So I'm going to plug in n equals 0 first. And this says that C1 times 2 to the 0 plus C2 times negative 1 to the 0 is equal to 0. Okay, and let's just rewrite this. This is saying that C1 plus C2 equals 0. Okay, so they add together to be 0. And now I'm going to plug in n equals 1. And this says that C1 times 2 to the 1 plus C2 times negative 1 to the 1 is equal to 0. And that tells us that 2 times C1 plus negative 1 times C2 is equal to 0. And now just focusing on these two equations that we have, now you can reason out that this implies that C1 and C2 are equal to 0. These are just two lines intersecting in the C1, C2 plane, and they intersect at the origin. So C1 and C2 are both 0. However, I want to think about this in matrix format. So I can rewrite this as a matrix equation that looks like 1, 1. So those are the coefficients there. And 2, negative 1. I'll move so you can see in a second. So I have this matrix multiplied by C1, C2 must be 0. That's exactly what these two equations are saying. Okay? This matrix is literally just coming from powers of 2 and negative 1. So this is 2 to the 0, this is negative 1 to the 0, 2 to the 1, negative 1 to the 1. And if we had more values of r coming from a higher degree polynomial here, we would just have another row on this. Okay? And each row would have 3 entries. And this is something where this is just generally going to be true. And I want to say that if these two values are different, then this matrix will always be invertible. And if this matrix is invertible, then I can multiply by its inverse on both sides. And we get that C1, C2 must be 0. Or the inverse of this matrix multiplied by this 0 vector will always be 0. And so we get C1 equals C2 equals 0. So if a linear combination is equal to 0, then the coefficients must be 0. These two must be linearly independent. Okay, so we have two linearly independent solutions. And I want to say that this forms a basis of the set of solutions. We know the set of solutions is a vector space. We have two linearly independent solutions. And I want to say that this space is two-dimensional. Therefore, this is a basis. Okay? How might we go about doing that? Okay, so I want to call the set of solutions S, and I want to define a linear function I'll call it F, from S to R2. Okay, so this map is going to be I'm going to take a sequence. So I'm going to take a sequence, I'll call it Bn. And I'm going to map the sequence to the 2D vector in R2, which is just B0, B1. Alright, and now I want to look at some properties of the function f. So, to start out with, I want to say that f is onto. Okay, how do I know that f is onto? Well, suppose I want to hit a particular vector here, b0 and b1. Well, I can just set the first two terms of the sequence to b0 and b1. How do I know that produces an actual sequence, bn? Well, I can get b2 by doing b2 is equal to b1 plus 2 times b0, and then I can get b3 by doing b2 plus 2 times b1, etc. So we can keep finding the next term of the sequence, and then we just have an entire sequence. That is my sequence which maps to the point b0, b1. So I can always create a sequence which maps to any particular 2D vector that I want. So f must be onto. Now I also want to say that f is 1-to-1. Okay, how do I know that f is 1-to-1? Well, let's just find the kernel. So something I didn't talk about in the kernel video, but f is 1-to-1 exactly when the kernel is 0, and that comes from the rank nullity theorem. So what is the kernel of f? Well, the kernel is the set of sequences such that this ends up being 0. So it's the set of Bn such that both of these entries are 0. Well, how many sequences have the first two terms equal to 0? Well, if the first two terms are 0, then I can find the second term, b2, by just doing b0 plus 2 times b1, and that's 0 plus 2 times 0. That's going to give us 0. And the third term is going to be, again, 0 plus 2 times 0, and then the whole sequence must then be 0. So this is just the 0 sequence. Okay? Another way of saying that is the dimension of the kernel, the dimension of the null space essentially, is 0. Okay, so remember the rank nullity theorem says the dimension of the null space, I'm going to write that as the kernel, of a transformation, plus the dimension, I'm going to run out of space here, plus the dimension of the column space, which is known as the range, is equal to the dimension of S, the dimension of the domain. Okay, well, we just said that the dimension of the kernel is 0 because it only contains the 0 vector. The dimension of the range is 2 because f is onto, and we have a two-dimensional space that we're going into. So this is 0, plus 2, and that is equal to 2, so the dimension of S must be 2. Okay, we have a two-dimensional space of solutions. So when we have two independent solutions here, that must form a basis. So S the set that we're trying to find must be equal to the set of linear combinations of xn and yn. All right, so in general, this argument is going to work for any problem that we do. And what it's going to say is that the dimension of the solution set is going to be equal to the order of our linear difference equation. Okay, so you don't have to do this step each time. Just remember that the difference between these two indices, the biggest one and the smallest one, which in this case is 2, is the dimension of the solution set. And so if you find two linearly independent vectors by having two distinct r values here, then you have a basis for the solution set. We're now going to take a look at a linear difference equation that falls into one of the other categories. It's still homogeneous, but the auxiliary equation is going to look a little bit different. Okay, so we're going to skip a lot of the steps that we had before. In particular, I'm not going to write down our guess. I'm going to jump straight to the fact that we want to look at r squared minus 4r plus 4 is equal to 0. And I'm getting that from just copying down the coefficients here and making sure the signs are also matching. Okay, so this equation factors as r minus 2 times r minus 2. Okay, so what does that mean? Well, in particular, if r is equal to 2, then these both will be 0. So 0 times 0 is 0, which means that r squared minus 4r plus 4 will be 0, which means that the solution xn equals 2 to the n will be will satisfy this this difference equation. So what's the problem here? Well, the other value of r that we get is also 2, and if I wanted to try to say something like yn is the other 2 to the power n, these two are not linearly independent, and so they do not form a basis. But our argument to say that the set of solutions should be two-dimensional still works. So I need some other solution which is linearly independent from these. Okay, so this is the wrong guess. Okay, but again, lots of smart people have already studied this, and there is a good guess to use here, and that is n times 2 to the n. So whenever you have a repeated root, specifically with multiplicity 2, then here are two linearly independent solutions. Okay? So it's not obvious using our auxiliary equation that this will actually be a solution, so let's run through that check real quick. So what does it mean to check this? I need to plug it into the original equation and make sure I get out 0. Okay, so the nth term is n times 2 to the n minus 4 times the n minus first term, which is n minus 1, times 2 to the n minus 1, and then plus 4 times the n minus second term, which is n minus 2 times 2 to the n minus 2. Okay, just like when we originally created our auxiliary equation in the first problem, we have something here where there's a bunch of factors of 2. We can factor those out. So this is going to be equal to 2 to the n minus 2 times some stuff. So what's left here is I had n factors of 2. I pulled out n minus 2 factors of 2. There's still 2 left. So 2 factors of 2 is 4. 4 times the n that's still there. So this is 4n. The second term here, I'm pulling out all but one of these factors here. So there's going to be 1, 2 left. And there's going to be a 4. 2 times 4 is 8. And then I have n minus 1. So 8 times n minus 1. Okay, I'm pulling out all of the 2's here. So there's still this 4 times n minus 2. So what is this? Well, this is 2 to the n minus 2. That part's not 0, so hopefully this part's 0 so that the whole thing will be equal to 0. And I'll leave it to you to check that everything works out here. Or let's just do this really quickly. I have 4n, 4n, negative 8n. All the n's go away. I have minus 8 times minus 1 is positive 8. And I have 4 times negative 2, which is negative 8. So the constants go away as well. So the whole thing is something times 0, which is 0. Therefore, yn is a solution. So our solution set looks like this. It's the set of linear combinations of these two solutions. Okay, so that's our answer. And I will say that technically our answer should be a set of sequences, and our sequence notation has parentheses around here. I'm not going to be picky about that ever. As long as you have this basic format where you have linear combination, then you're good. So you might be curious what happens when you have a triple root, and it turns out that this multiplying by n thing is also going to work there. So I'm not going to do this full example, but I will say that if we had something like this, okay, so if we had something like that, oh, actually, let's make these pluses. Then we're going to get the auxiliary equation. Looks like this. Okay, and this is exactly r plus 1 cubed. In other words, we're going to get r equals negative 1 with multiplicity 3. Okay, and our 3 solutions that are linearly independent are going to look like this. We're going to have negative 1 to the n times negative 1 to the n, and n squared times negative 1 to the n. We're now going to go back and talk about one more thing you might be asked to do. So just recall we had this, and this was our solution. Okay, so this is the set of possible answers to this. So another way of saying that is a sub n equaling this is called the general solution. Okay, so the general solution has constants here, and they can be any real numbers, just like they are in this set. Another thing you might be asked to do is to find a specific solution, and the way this is normally phrased is you are given initial conditions. So here we're asked to find a solution, one particular solution, to this exact same LDE, but we also want it to satisfy the fact that A0 is equal to 3 and A1 is equal to 2. So how do we go about doing that? Well, we do the same steps to get to this point right here, or equivalently this point, and then we do one additional step, which is to find particular values of C1 and C2, which make this happen. So the solution to this involves finding the general solution, then find the values for Ci. Okay, so we have an is equal to C1 times 2 to the n plus C2 times n times 2 to the n in this case. And we want to plug in specific values for n. In particular, this thing should hold for all n greater than or equal to 0, which includes 0 and 1. So I'm going to plug in 0, and then I'm going to plug in 1. So this says that a sub 0 is equal to C1 times 2 to the 0 plus C2 times 0 times 2 to the 0, just replacing all the n's with 0. Okay, well, a sub 0 we're told is 3. So this is the same thing as saying that 3 is equal to, this is just C1 times 1 plus C2 times 0. In other words, just C1. Okay, we're also told that A1 is 2. So we're going to plug in n equals 1, and that's going to tell us that C1 times 2 to the 1 plus C2 times 1 times 2 to the 1, and that has to be equal to 2. So 2 is 2 times C1 plus 2 times C2. Alright, so we can simplify this by saying just divide by 2. So we have two equations here. We have this and this. It happens to be the case that this is a fairly simple equation. It's just one of the variables already solved for. But in general, we're going to get a system of equations here. And you already know how to solve systems of equations, and you solve that in order to find the values for Ci. So in this particular case, since C1 is 3, this tells us that 1 is equal to 3 plus C2. Therefore, C2 is equal to negative 2. Okay, so we have C2, we have C1. Therefore, our specific solution is a sub n equals C1 times 2 to the n plus C2, I'm going to write that as minus 2 times n times 2 to the n. So that is one specific solution to this LDE, which satisfies the fact that if you plug n equals 0 in, you get 3. If you plug n equals 1 in, you get 2. Alright, I'm going to refrain from doing the case where the auxiliary equation gives you a non-real root for now. Thank you for watching.